Morning. I'm good. We're almost ready. Oh, the microphone. Ah, okay, because.
Zoom, the people only see the camera.
Cheers. Shall we? Okay. So, good morning, everybody. Welcome back. So, the plan for today is the following. I mean, first, let us recap at which point we arrived yesterday. Okay? So, I hope that I convince yourself, that we have some motivations which are very concrete to try to study particle physics phenomena with quantum computing and quantum simulation, finite density, and out of equilibrium dynamics. We have already seen some concrete models, which were also the basis of some of the exercises I've given you, this U1 quantum link model and this Z2. Today, what we will be doing, we will introduce yet another model, which is more motivated from the point of view of introducing fermions in the dynamics. It's called the Schwinger model. The Schwinger model is equivalent to quantum electrodynamics in one spatial dimension. Then we will have a review of what are the methods that people have developed in these last 10 years to realize gauge theories in quantum simulation and quantum computers. These are really, I mean, more theory methods. And then we will see a concrete example, which is the realization of the Schwinger model with trapped ions in a digital quantum simulator, a quantum computer. Which has been, I would say, the first experiment which has really put a connection between particle physics and quantum computing / quantum simulation. Okay? So we start with the Schwinger model. Okay, this was our example number 3. We had the 2 first. This was the 3rd. So the Schwinger model requires us to have a spatial lattice, which is now one-dimensional. And on this spatial lattice, we do the following. We will put matter fields on the vertices, and then gauge fields on the bonds. Okay, this is matter. This is gauge. Now, since it has to describe quantum electrodynamics, the first problem is we have to understand how to introduce both electrons and positrons. Okay? Because we want to have matter and antimatter, of course. Okay? And the way to do that, or one possible way to do that, is to introduce what are so-called staggered fermions. And these staggered fermions, they work like this. Okay? We have to put a table. So we have a single field, which is psi, that lives at the site x. Okay? And then we do the following. So if the site is even, we say that when the site is full, we have an electron, and when the site is empty, we have the vacuum. Okay. And instead, when the site is odd, we kind of do the opposite. So if the site is full, we have nothing. If the site is empty, we said that we have a positron. Okay? So a positron is a hole on odd sides, and an electron is a particle on even sides. Okay? Now, can we write down a corresponding number operator? So yes, of course. So the number of particles, this is equal to the sum over all the x of -1 to the psi dagger, to the x, psi dagger x, psi x. And this -1 to the x is due to the fact that having a full site is not always corresponding to a particle. It depends on the parity, plus a constant, which is plus 1 minus -1 to the x divided by 2. Okay? Let us check if this makes sense. If x is even, this is plus, this is 0. So having a particle is equivalent to having a full site. Instead, if x is odd, this is -1. So this becomes +1 minus this. So if this is equal to 0, then we have a particle. If this is full, we have nothing. Okay? We can, of course, also write down the corresponding charge operator. Rho. And this rho, what does it do? It has to count negative if there is something here, because the electron has negative charge, and positive if there is a positron on the even sides, and one can do the math, and the corresponding thing would be equal to something like this. Okay? Psi dagger x, psi x. So this is the negative charge. So the electron we count as a +1, so plus 1/2, and here we have -1 to the x -1. Okay? Yes. Okay. So this is so-called staggered fermions. You could tell me, okay, in principle, we can introduce also other fermions. We can just put spin-full fermions and interpret spin up as an electron and spin down like a positron. That would be one way. But then it will be very complicated to understand what particle annihilation and creation is. Instead, we will see that with the staggered fermions, this is very easy. Okay? Actually, we can see it already now. Okay? So imagine that you have a lattice of 4 sides. Okay? And the configuration of our particles is the following. You have full, empty, full, empty. Now, what is the corresponding state of the fermions? Well, the first site is odd, it's full, so there is nothing, it's a vacuum. The second site is empty, it's even, it's also vacuum. And you can do the following here. Okay? So what is a null state for us will be what we call bare vacuum, or fermion vacuum. Okay. Let's do another example, when instead of having this, we have something. We have this. Okay? The first site, so vacuum. But now the second site, it's on an even site and it's full. So here there is an electron. And then on the third site, which is odd, there is nothing. but not odd if there is nothing. This corresponds to a positron. Okay? And here, this is also empty. So that will be the equivalent of an electron-positron pair. Okay? Yes. Yes, I will do it. This one? Okay. So here we are trying to reinterpret this state utilizing this table. Okay? So the first site is odd, and there is a full site, so it corresponds to the vacuum. Okay? The second site is even, but now it's full. So this corresponds to an electron. Third site, odd, and is empty, positron. Okay? Fourth site like this. We can also do, of course, you can also do other states. Eh? For instance, you can have a state where you have something like this. You have 3 occupied and 1 empty. Okay? And this is a state which, again, here will be 0 and 0. Here you will have an electron, and this will have vacuum. So this is an electron in vacuum. There is a state which has a net charge. So if you compute the sum of the charge over all the site, this will be +1, and so on and so forth. Yes? Yes? Oh, this is sum over x, sorry. X. So this is the global. Sorry. My n and my x are very close. Okay, cheers. Okay. So this is how we introduce fermions. Now, we have to introduce the gauge fields. This requires a bit more work. And for this, I want to cancel this part. Any more questions on this? Sanger fermions. This looks like a trick to put particle and antiparticles on the lattice, but actually it's, first in one dimension it works very well, but it's also something that is used also in nowadays lattice QCD simulations. Many of the largest scale simulations are done with staggered fermions. So it's a concept that is good that you know even beyond what we are doing. So now we have to decide how to represent the gauge fields. And since we are interested in the U1 group, one option is to use the T group, so the T group, which is the circle. So essentially, our gauge field will be described by 2 operators. One operator that tells us where we are on the circle, and another operator that moves around the circle. Okay? And this operator we call theta. So sorry, e to the I theta. Something. So if we have a state with a given value of L, if I apply e to the I theta, then it changes the state by an angle. And if we apply e to the I theta with a minus, then it changes in the opposite direction, of course. Okay? So this is our U1 variable. This theta is sometimes called parallel transporter. Sometimes it's useful to imagine that on each bond there is a particle that is really span the configuration space of the gauge field. Okay? And the idea is that these 2 operators are not generic operators, they have to satisfy specific commutation relations. And the commutation relations that one imposes are the following. Let me use the hat, which at some point I will drop, but here I would like to keep them. So the commutation relation between theta and L is such that this becomes a delta function. Delta and M. Okay? So they commute. that they don't commute. L, if you want, will be the equivalent of our electric field. Okay, at the very end, this is our electric field. So now we know what we have on the vertices. We know what we have on the bonds. What do we have to do? We have to find out what is the gauge invariant Hilbert space. So the set of states that are physical. Okay. Hilbert space. Yes. Oh, they correspond to the bonds. Okay. Actually, yeah. So yes, they correspond to the bonds. Sometimes I will use N and M. Sometimes I will use a different indexing, which is N, M plus 1, M, M plus 1, in the sense that the indexing will be such that this guy here, sometimes for brevity, I just label it with a link on the left. Sometimes I put explicitly that this is on a specific link. That's what they meant here. Yes? No. It's you in principle have more freedom. You can choose different representation of the U1. You don't have necessary to have a circle group. You can choose a representation, for instance, that is not compact. Okay? That is really R. And there will be different operators. Later on, we will choose yet another representation where instead of using this, we will use spin variables. Okay? So this is just one possible one possible way of putting the theory on the lattice. Okay? It's not unique. We will see it later. We will see it later. So the commutation relation between the electric field and the parallel transporter, they cannot. Okay, so at some point there will be a commutation relation between electric field and really what transports parallel this has to be fixed. This is fixed by the gauge symmetry. But there will be other conditions, like a unitarity of the parallel transporter that might change with respect to the representation. They are not important, let's say. But this is, I will discuss this later, so for a moment, put it in parentheses. So now we want to write down the gauge invariant Hilbert space. Okay? So first thing we have to define is Gauss law. Okay? So how do we write down Gauss law? We really take the one that we know in the continuum, and we try to approximate it. Well, approximate it. We just replace it with this kind of things. Okay? So in the continuum, we have the variance of the field. This is kind of essentially a discrete derivative on the lattice. And we can imagine that if we have, for instance, a point X, and here we have our two electric fields, the derivative of the field, this will be the electric field on the right, so between X and X plus 1, minus the electric field on the left. X minus 1, X. We're essentially doing a discrete derivative on the lattice. On the other side, instead, we have to put the charge operator. Now, the charge operator is not just a number of particles, because we have seen the charge depends if we are even or odd. Okay? So here, we really have to put this equation. And this will be equal to psi dagger x, psi x, plus 1/2 minus 1 to the x minus 1. Okay, yes. Ooh. Okay. Maybe I want to make a comment here. Okay. So in principle, the derivative you can, when you discretize a field on lattice, you can actually choose in which direction you take the derivative. Okay. This is just an overall phase. For the purpose of my notes, let me use a different notation. So I will actually use here a minus and here a plus, but it doesn't matter. Okay. Everything is actually invariant under that, but I have all the cartoons with this notation, so I will have to keep that. Okay. Okay. So this is now our Gauss law. So now we have to write down the states which are allowed. Okay. And this is pretty simple, but since we have this weird -1 to the x, let me do it separately for the even and the odd sides. Okay. So on the even sides, so suppose that I have an electric field entering here which is given value, alpha. Okay? Now, on the even side, this is 0. So suppose that now you have a full side. Having a full side on an even side, this is equivalent to having an electron. Now we can read off the value of this electric field. This will be equal to alpha plus 1. Okay. Oh, no, sorry, guys. I have to say this was correct what I wrote, and I messed up my own. Let's keep it like this. This is alpha minus 1. We have a sink here of electric field, of course. Okay. So there is an electric field entering here, sees a charge, the electric field decreases. Okay. Sorry for the change of notation on the fly. Now let's do the same thing. Instead, if we have alpha, and here we have an empty site. If here we have an empty site, what is happening is that the part on the right is equal to 0. Okay? Because this is 0 and this is 0, or even x. So the two electric fields have to be the same. Okay? So alpha is equal to alpha. So this is our gauge invariant Hilbert space on even links. Even sides, sorry. We can do the same on the odd sides. On the odd side is a bit more complicated, yeah? Because you see that here we have a -1 popping up. Okay? So if we want to write down the equation explicitly for the odd sides, we have that E x plus 1 is equal to E x minus 1 x plus psi dagger x psi x plus 1. Okay? Sorry, minus 1. Okay? I'm just rewriting this with x odd. So what is happening here is the following. If I enter here with a flux, electric field flux alpha, and I have nothing, this is 0, but I get a -1, so this has to become alpha minus 1. No, wait. There is something weird. Okay? Of course, there is something weird. Okay, let me try to fix this. This is okay. I messed up one sign. Now I need to find out where it was. Okay. Sorry? Is a positron. Yes. But then this electric field has to increase. I think what I messed up is that here there was. Yeah, there was a plus. Yes? No, psi dagger. So psi is actually counting if there is nothing or something. It's not counting whether there's a particle or not. Okay? So this on the even sides, sorry, on the odd sides, this is the state where psi dagger x psi x is equal to 1, and this is where it's 0. Okay? Because the charge and the number operator, they are not linear. They are linear function of psi dagger psi, but you need to have take into account these corrections. Okay? So I think here what I'm messing up is that here there was a minus sign. Okay? Sorry for that. So this becomes +1. And indeed, this gets now correct. Sorry for this. And now, then you can do the same, of course, when... No. Guys, no, sorry. Okay. This was minus. I've messed up the electrons then. Okay. So let me do it properly. So this is alpha, positron, alpha -1, and this is alpha. If this is 1 minus 1, this is alpha. Okay, these are correct. Okay. And here, the Gauss law didn't have this. Okay. On the even sides. So next time I will write it again also for that. And here we have a +1. Okay, I'm sorry for that. Somehow there was a minus sign fluctuating. And here it's plus. Okay? Yes, exactly. Exactly. Because then it decreases when it crosses an electron, and it increases when it crosses a positron. Good. So that's the gauge invariant Hilbert space. It's a bit more complicated than the one we had yesterday for the quantum link models, because it has to involve both matter and gauge fields. And is, of course, infinite dimensional in the sense that the value of alpha, it's a continuous variable. Okay? It's a continuous electric field. So it can go from 0, 1, 2, 3, and so on and so forth. Okay? So there is no bound. Now there are, yes? So the value of the electric field seems to depend on the representation. Or continuous. Okay, no, wait, it's a bit different. No, the value of the electric field is always, sorry? So you can quantize this problem, okay? And then choose a representation where L eigenvalues are just integers, okay? But of course, this is not bound, okay? This is what I want to make a statement. Of course, you can also quantize this problem in the basis of theta. This will be kind of a momentum for this particle, but that's not useful for us because Gauss law only depends on L, and you want to have something where it's easy to identify the states with different electric fields. Okay? Good. So now we need to have some non-trivial dynamics that lives within this gauge invariant Hilbert space. Okay, that's really the last part. I wanted to keep, let me keep this table for a moment. Okay. And I also keep this too. Dynamics. And let me write what the corresponding dynamics is, and then we understand piece by piece what this represents. So the first term will be something which very much seems like a tunneling, so the sum over all the possible sides, I from 1 to n minus 1, of, let me use x, psi dagger x, e to the I theta, x plus 1, psi x plus 1 plus Hermitian conjugate. That's the first term. Then we will have a term which is plus g squared divided by 2, sum over x e, which is equal to our L. Let's L x plus 1 square plus m sum over all the x minus 1 to the x psi dagger x psi x. Okay. So this is the microscopic Hamiltonian that one can propose for describing the Schwinger model. Now let me tell you what these terms are. Okay. The last term is easy. Is a mass term essentially. Okay. Essentially counting whether we have particles or not up to a constant. Okay. This is what we call mass term. The second term, since L is essentially our electric field, this is nothing but the electric field square term. Okay? is the term in the Hamiltonian that we will get in electrostatics. Okay? And now the first question comes, okay, but this is weird. Typically in electrodynamics, we are used to have something like this, right? Not this only. Why there is no magnetic field here? What is the reason? No, the organizers are not allowed. I don't want to. What is the reason why we don't have a magnetic field term in this Hamiltonian? Think about it. Is there a magnetic field in one dimension? No. Magnetic fields in one dimension do not exist, right? You need at least 2 legs of a ladder to define a magnetic field, because you need to move a charge around a plaquette to generate a magnetic field. Okay? In one dimension, magnetic field terms are absent. And then there is the first term. So the first term describes the coupling between, I mean, this is just electric field, this is just matter. This describes the coupling between matter and gauge fields. Okay? So it's really the equivalent of what we will have called minimal coupling. Okay? And let us show how this is actually acting on possible states. Okay? And I do it as follows. I can replace it this here. And okay, take a state which is alpha, an electron, alpha plus 1, positron, and after a positron there is alpha. Okay? So this term, what it's doing is tunneling or exchanging this particle. So this implies that here there will be nothing, here there will be something, but of course this is like a vacuum. And we will change the value of the electric field in the middle, and we'll make it equal to alpha. Okay? So this is the application of HT, this term, on top of this state. Okay? Yes? Okay. No. Okay. Something like this. That's what you want to have. So this is what you mean. If you move a particle, an electron here, it moves around. Yes, you can create a global magnetic field. No. This will be a global magnetic field. Okay? This will not be a local magnetic field. So it's not B square, but what is so-called, if you want, it's a variable, which depends on how many times your charges have moved through the ring. But it's actually a topological quantity, okay? Because it depends on the topology. I mean, if you have a ring, you have it. If you have it on a line, you don't have it. It's a boundary condition only. This is not something that will enter here. Okay? If that's what you meant, right? That you can generate a magnetic field by moving a charge along a ring. No, an infinite string, you don't generate any magnetic field, I'm sorry. No, but the current has to close. Right. Okay. Well, it's tricky. I don't know. I mean,
No, because I was.
It's a kind of a boundary condition effect.
Okay.
That's the point.
Okay.
So, yes. No, of course, because the gauge field is defined also out of the plane.
Ah, okay.
I mean, here the gauge field has to define at the bond, okay? The magnetic field has to define at the available gauge fields.
I was thinking...
You were thinking about this.
Exactly, yes.
Okay. There are, maybe this is something that can clarify your point. In principle, you can also define a gauge theory where the electrons move only in one dimension, but the gauge field lives in 3D. Okay? This is also possible. It's perfectly legal. And these gauge theories are a bit more weird. Okay? And there, of course, there is a magnetic field. Okay?
Can I have a question?
Yes.
Marcello? So the last term, I mean, how do you do the continuum limit and recover some sort of a Lorentz invariance in general?
Very good. Okay? Because they said, okay, we are breaking translational invariance by one lattice spacing. Okay? Well, we have actually broken it in the definitions, okay, already, and in the Gauss law. This is broken everywhere. This implies, then you can say, okay, what the hell? That's okay. I mean, so this breaking, it's not something that prevents you to take the continuum limit, but it's something that requires care. Okay? So in principle, if you want to take the continuum limit, this prefactor here will have the lattice spacing inside. This will have the lattice spacing inside, and this will also have the lattice spacing inside. And you will see that I think M actually has the lattice spacing with the power 1. So this implies that this goes down to 0 when you take the thermodynamic limit. Okay? But you still have to keep it because it's, of course, at every finite value of the lattice spacing, this is finite. Hmm? Yes. Yes.
You are not tunneling particles, but tunneling the representation of the particle.
That's correct. Yeah.
Tunnel a particle, we have to move two times.
Very good. Excellent. So the question is essentially, how can we let an electron move? Yes. Okay. The electron moves through the creation of particles and antiparticles. Okay. So if you want to have a state where you have an electron at a given site, and you want to have a final state where the electron is here, the intermediate state is actually a creation of an electron-positron pair here, and then you annihilate these two. Okay? Yes, exactly.
In the Hamiltonian, we just have annihilation.
Exactly. There is no direct... No, there is also creation. Because, of course, this term acts in this way, but if you apply this term on this, then you come back. Okay? So the Hamiltonian, as it is written, only contains particle-antiparticle creation. Okay? It does not create, it does not contain any kinetic energy of the particle. These are really true virtual processes. Okay? Which is very counterintuitive. Okay? It's a lattice, but this is the reason why, I mean, it's a lattice representation. You should really think about it at the very end towards a continuum limit where there is a kinetic energy of the electrons and positrons. Hmm? Any more questions?
So historically, I mean, what was the motivation of Schwinger to introduce this?
Okay, yeah. First of all, Schwinger did not work on this, did not formulate the lattice version, okay? So Schwinger studied quantum electrodynamics in one dimension and the continuum only. The reason why he was interested in this is that he found out that there are regimes where this is exactly soluble. And at that time, we are in the early 50s. These were the days where quantum electrodynamics was born. And quantum electrodynamics in 3 dimensions is not soluble. Right? It's already a relatively complicated theory. And Schwinger was hoping that by formulating in 1 dimension, you could learn about generic properties of gauge theory, or abelian gauge theories of electrodynamics in lower dimensions, in higher dimension later on. So it was kind of a, we'll say, toy model. The interesting thing of this, I mean, it's not a toy model which is not particularly meaningful. It has a lot of phenomena which are relevant also for quantum chromodynamics. It does have confinement. We will see it later on. There is chiral symmetry breaking. There are many effects which also appear in more complicated theories. Of course, Schwinger didn't know at that time. We are in 1950s. He had no idea that quantum chromodynamics existed. Okay? Actually, the only gauge theory that was formulated until then was abelian. So there was not even Young-Mills. I was just interested in the model. Yes?
Applying a lattice model, like
now we will see. We will see it. This depends a bit on the type of experiments that one has in mind. Okay, so let me also mention, so this is one of the equations that now we will see how to put on a quantum computer. I would like to mention that in principle you can also do something where instead of using this parallel transporter, you use a finite dimensional Hilbert space. Okay? So this is what people will call Wilson lattice gauge theory. But you can also do the quantum link model. And to do the quantum link model, what you have to do? You have to replace the electric field with an Hilbert space, which is the one of a spin. So instead of having a circle, you now have maybe only two values. Okay? Can be a spin 1/2, can be a spin 1, who cares? And then in this language, the u, which is equal to the I theta, they will become S plus, and u dagger, this will become S minus. Okay? So this is the thing that you do, and in the quantum link, the term that we add up there will become something which is of this type, and the electric field term will become something where you have a z square, and the mass term, okay, the mass term is the same because all involves the matter. Okay? Dot, 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 dot. Okay? So now, in the next 45 minutes, I would like to show you two different ways of putting this on a quantum computer and this on a quantum simulator. However, before doing this, we need a bit of more abstract theory. So let me stop now. I mean, are there questions? More questions on this? Because now we change a bit.
You are discussing this one-dimensional?
Yes, this is so far everything in one dimension. This will be, yeah.
We discussed this one-dimensional model,
Yes.
but when you described the quantum link model was on the plaquette and it was
Yes.
a b-dimensional model.
Yes, in principle, I mean, we could easily extend this to 2D. I mean, if you want to know,
Okay.
I can tell you.
So in the quantum link model now we can have a magnetic field?
Yeah. I mean, we can also have it in the Wilson. I mean, the idea when you go to 2 dimensions is that in order to have a magnetic field, you want to have a charge moving around. So this will be at the end something where you have a trace of your plaquette operator here, and the plaquette operator, this is really e to the I theta. Okay? That will be a magnetic field term. In the quantum link model, this will be the same magnetic field that we have written yesterday. So this is plus, S minus, S plus, S minus. Okay? So introducing magnetic fields is actually very cheap, but the reason why I'm not doing it is because we will discuss implementation where these are not present. Why?
Okay.
Let me tell you why.
Why?
Because they are very hard. Okay? It is very hard to write down a microscopic implementation where you have a 4-body interaction. Okay?
But it's easy to control in the lab to avoid magnetic fields.
Well, avoiding it is easy because you just don't care about it. Its coefficient is 0. It's not there. But then the question is, of course, what does it mean in 2 dimensions to have a theory where you have only E squared but you don't have B squared? Then you should wonder, okay, what is the physical relevance of that model? And this is non-trivial. It's a non-trivial question.
Because there is some kind of symmetry between magnetic field and electric fields. You just gauge them one in another. So.
No. Okay, the gauge symmetry does not care. I mean,
not this gauge in this sense, in this sense, but you can just see a magnetic field like C times E. So you can transform, and the Maxwell equations can be invariant in the vacuum. So.
In vacuum, yes.
Yes, but now we have
Okay.
matter.
Now there are charges. I mean, of course, there is a deep relation while you have E squared. There is a deep reason why you have E squared plus B squared in quantum electrodynamics. Okay? It's also related to Lorentz invariance, blah, blah, blah. But this is unrelated to gauge symmetry. So gauge symmetry, in principle, you could have a coefficient here alpha and a coefficient here beta. And for arbitrary value of alpha and beta, this is gauge invariant. So putting the magnetic field to 0 is not something that affects gauge symmetry. find something that affects other properties. Okay? Yeah.
Okay. Thank you.
Cheers.
So, so then this SZ, S plus, S minus is like how you would map it to a spin model, right?
Yes.
But then like how should I think about L and like the original model? Like is it just an electric field at every point or?
Yes.
Okay.
Yes.
Okay, I see. Okay, perfect,
Yes.
thanks.
So this is really reading off the electric field at every bond. Yeah. Any more questions? Nope. Online.
So it's not completely clear to me how theta and L relate to the alpha that we have in the diagram.
Oh, alpha is the eigenvalue of L.
Okay.
No, it's not, sorry. So here you have a state, alpha L equal to alpha. Sorry.
Okay. But then the hopping is coupled to theta.
Yep.
So how
Theta is something that changes the value of L.
Okay.
So, shit, I canceled the example. So in the example, we had this particle and antiparticle. And when we apply the tunneling, we also have to change the value of this L. And in particular, in that case, we have to decrease it.
So
Okay? And we decrease with e to the I theta.
So e to the I theta is like the translation operator for L.
Exactly.
Okay.
Exactly. Is
Thank
what
you.
moves. Other questions? No. Good. Oops. Now, how do we realize these theories? I mean, I will now give you a brief review of what are the generic methods to realize a gauge theory, and then we will see one in detail. Okay. And the main challenge in realizing gauge theory is that we have to impose, we have to impose a very strong constraint on the Hilbert space. Okay? So the goal for us is constrain the Hilbert space to what we have a physical Hilbert space, which we have written yesterday, is a set of states such that when we apply Gauss' law to these states, we have 0. Okay. So this is really the thing that we have to do. Then, on top of the Hilbert space, then we have to realize the dynamics. But actually, realizing the dynamics is typically easy. What is hard is to get the correct Hilbert space. And here there have been many proposals. Okay? The first proposal, which is something which people have also used in condensed matter, is to utilize what are so-called energy penalties. Okay? And here the idea is very simple. Instead of realizing directly these Hamiltonians in the lab, what we have initially an Hamiltonian, which is U sum over all the vertices or all the sides, gx squared, plus another Hamiltonian h prime, h, which depends on coefficients lambda. So that's what we realize in the experiment. And then what we do, we take a regime where U is positive and much larger than lambda. Okay? When we do that, the low energy physics is dominated by states where G applied to those is equal to 0. So we are automatically working. We work directly on H physical. Okay? Yes? Yeah. Yeah. At all feeling, yes, yes.
But then you get
Excitation.
yes. No, not excitation, but you'll have effective dynamics
which explores the, yeah. Yeah. No, wait. The point is then you have an effective Hamiltonian, okay? H effective, which will be something which is H, and the coefficients will be of order, let me call it H prime lambda prime, where lambda prime is of order of lambda squared divided by U, or higher orders. So okay, that's the second order perturbation theory plus ... Okay? In terms of physics, of course, what is happening is that if we look at the spectrum of our theory, there will be low energy states here. These low energy states, they are actually living in the gauge invariant Hilbert space. And then there will be states which are separated in energy by U, and this will be gauge variant states. So if you actually inspect those, the first band of those is a band of state where there is one GX, such that psi, when we apply to psi, you get 1. Okay? Then there will be another band where there are 2 points where you are violating Gauss law, and so on and so forth. Now, of course, if you look at this dynamics, this is something which is driven by what? It's driven by terms which explore this manifold and then come back. Okay? It's like every time when you do perturbation theory, you are always exploiting the fact that these matrix elements are actually dependent on the specific structure of these states. Okay? But that's fine, because they're only virtually populated. Okay? So if, for instance, in these models, if you compute, and in these techniques, if you compute the expectation value of the Gauss law operator, okay, as a function of 1 divided by U, you will see that this actually decreases with a parabola, 1 over U squared, if it's second order perturbation theory. Okay? So it's as a function of 1 over U squared, this is decreasing linearly. Okay? So this implies that you have a very controlled manner of realizing a gauge theory in the infinite coupling limit. Of course, you will never take an infinite coupling limit. First, because probably your microscopics blows up before you do that. But also because by taking the infinite coupling limit, you are making the parameters of the gauge theory going all to 0. Okay? So you will be sensitive to dissipation, to everything else, because you are slowing down the dynamics. Typically, what one would like to do in experiments is to have a reasonable value of which is maybe 10 to the minus 2, 10 to the minus 3, and then work on that. Okay? On that level. Okay. Now, what is nice about this energy penalty is that this is actually very generic. Okay? In principle, here we can put color indices, blah, 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 and this will work directly. I mean, we are not relying on any specific approximation. And we will see later on, or maybe early tomorrow, one application of this. I would say that this is by far the most used method. Yes? Yes. Yes. Excellent question. Excellent question. Okay. If the theory is abelian, typically yes. Because we have seen that, I mean, essentially it's, we have to make a state which is a product state, and product states are easy to initialize. I mean, we assume that they are easy to initialize. If the theory is not abelian, this is not true. Actually, this is a problem. The initial state, because it's never a product state. If the theory is not, it can be a product state, but it's never diagonal. Okay, so you have to engineer singlets. Hmm?
Sorry, I don't see the connection between non-abelian structure and like more difficult.
No, I can tell you. Okay. If you want to initialize something which is abelian, you just have to fix essentially particle numbers. If you want to have something non-abelian, even think about 2 spins. If you want to initialize something which is actually an eigenstate of S.S, you have to be extremely careful. Okay? It's not something which is a simple product state. You have to initialize it in a singlet. Imagine trying to do that, try to build a singlet between a fermion and 2 spins. Okay? This is not super easy if it's SU2. Imagine that you want to do the SU3. It's even more complicated. Okay, so proper initialization of gauge invariant state for non-abelian symmetry, it's actually a tricky business. What you typically do, I can tell you, or at least in the cases that I know, you try to first initialize small singlets locally, and then you slowly merge them. Okay? And if your dynamics is sufficiently slow, then they remain SUN invariant, blah, blah, blah. But this is definitely not something that you can do on every platform. Okay? It's very delicate procedure. Well, for abelian, I mean, you can do this, and then you are already working here, and then you let your dynamics work, and for relatively long times, this does not go away from the gauge invariant Hilbert space because of this reason. Yes? No? Very good. Okay, yes. Excellent question. Can I reformulate your question also for the people? Essentially, you are saying the following. Suppose that you are interested in very long time, because as I was mentioning yesterday, maybe thermalization is one of the things we want to study. Here we have our expectation value of G. What does it happen? That this monotonicity decrease or not? Well, in fact, if U is a huge scale, this will not decrease to 0. This will decrease at short time, but then will actually stay in a plateau until very long times. So this implies that we can actually, in principle, observe the full thermalization process with this method. And there has been an experiment in the group of Java Pan, where they have a small system, which actually, well, the system is not small, but it thermalizes relatively fast, over 5, 6 tunneling times. And they can do it exactly because of that. Huh? That when you protect the Gauss law, I mean, they protect Gauss law in a slightly different manner, but it's still energetics. And when you do that, there is in principle no problem. Of course, at some point there will be dissipation, and this will go down because of incoherent processes. Okay? But the coherent dynamics will not spoil it. More questions? Okay. So this is the strategy number 1. As I was mentioning, is by far the most used one. I don't want to cancel all of this. Okay. But yeah, can do it. Then, another method something is okay. Another method is actually to integrate out either the gauge or matter fields. And what does it mean is the following. Suppose, I mean, we want to study the model that we were looking at before, okay? And we had a given electric field at the site, let's say, left-hand side. Then we have a given population of the fermions, psi dagger, psi, at the given site. So what happens to the next electric field? That this is automatically fixed by Gauss law. So in principle, I can write down E1 and 2. This will be a function of only, let me write this as n, just for convenience, n1 and EL. So in principle, this is a mute variable. Then I can have this n2, which is free. But now what happens is that the electric field between 2 and 3, this is also not a free variable, because it's automatically determined by these 2, and so on and so forth. Okay? This is automatically determined by n2, by n1. And I can do this forever. So in principle, you can say, okay, let me forget that I have an electric field. I can write down a theory where I only include my fermions, and the electric field are integrated in a very complicated manner through a set of equations that, however, I can write down. We will write them down later on. So this is the idea. Of course, you can do this very same, forgetting about n, but just looking at the electric fields. So if I give you a system where I know the value of the electric field at every position, okay, the value of the matter field is automatically determined by Gauss law. I told you, I mean, earlier we have seen this example. If I tell you that here I have alpha, here I have alpha, and here I have alpha plus 1, you can tell me that there is an electron here and a positron here. And you also know that if I have alpha everywhere, there is no other particle everywhere in the system. So if you know all the values of the electric field, the matter field is redundant. In principle, you can decide that you integrate one of the two. Okay? This technique is very powerful because it keeps gauge invariance exactly. Okay? We are integrating it out. We will see that one of the price to pay is that the dynamics will be very non-local. The interactions will be very non-local, and the reason is that the more you go, the electric field will depend on the density of the previous matter and the previous electric field, but this electric field will depend on the previous one, and so on and so forth. So you will have a cascade of relations that, in one dimension, you can read them exactly. So in terms of analytics, this is fine. But in terms of experiments, this can be a huge challenge, non-locality. Then there is a third strategy. Yes?
The fact that you can integrate out one of the two, so does it tell something deep about the gauge theory? So it's a special property.
Okay, the fact that you can do it analytically, it might tell you something. Okay, it may tell you what is the effective potentials between particles. But in terms of, I would say, deeper insights, I don't think so. At the very end, this is just a consequence of Gauss' law. Gauss' law tells you that if you know the electric field everywhere, you know the charge everywhere. So it's something that you already know. You're just applying it. So yeah, that's what I would say is the thing. Then there is a third strategy, which has not been used that far, but I like to mention it because it's interesting, is to use what is so-called quantum Zeno effect, okay? So the quantum Zeno effect, it's an effect that is very famous in quantum optics, which is based on the following thing, is that if you have a system and you continuously observe some of its operators, you are actually inhibiting dynamics. Okay? The more you observe it, the less it evolves. And it's, of course, inspired by the classical Zeno effect. Zeno was a Greek philosopher that said, okay, let me try to let a turtle compete with Achilles on 100 meters. Okay? Do you know the story? How many of you know the Zeno paradox? Okay, no, then I explain it because I think it's important, okay? So Zeno said the following. This is 100 meters, and this is 50 here. This is 100. And who is competing? There is Achilles, and here there is a turtle. And Zeno said the following. Okay, the two guys are running, and we want to estimate who wins this competition. And Zeno said the following. They said, for Achilles, it's impossible to win the competition because the only thing he can do, as a function of time, at t1, he can halve the distance between him and the turtle. This is L Achilles turtles, LAT, becomes half. And the turtle has moved a bit. Then at the next step, he will halve this distance again. And then he will halve this distance. But you see, by keeping halving this distance, he never reaches the turtle. Okay? So ultimately, the turtle is bound to win every 100-meter race. Of course, this is not exactly how it works because time is continuous. Okay? In reality, so this reasoning does not apply. But that's the basic idea behind that. So every time you look, you are somehow freezing out part of the dynamics. And in quantum, there is the same thing. Okay? And in particular, what people have tried to propose is that if you have a measurement of Gx, which is very fast, continuously, and you start in a state which is gauge invariant, the expectation value of Gauss' law will not change. So even if there are terms in your Hamiltonian that will change will not commute with gauge invariance. You will actually suppress them dissipatively through measurements. Let me also say that I think these are very interesting theoretical ideas, but nobody's ever tried to do an experiment because it's, of course, very complicated. Okay? You have to precisely design a measurement that all involves links and vertices in a given manner, and it's not so easy. Okay? And then there is a fourth route, which is essentially what is called gauge building blocks. Okay? Which is actually a route that within itself has many different declinations. And the idea is the following. Imagine that you have two types of systems that can be two types of atoms or whatever. And each of them, at the level of a few building blocks, has a conserved charge. You can imagine that this is, for instance, a triple well. So here there are 3 sides here and 3 sides there, and the dynamics of these A and B particles conserve the numbers of A and B particles respectively. So here there is a U1 symmetry, and here there is a U1 symmetry. Now, if you try to combine these objects spatially, doing something like this, and let me use the other color, and something like this, and you combine them smartly, you are keeping a symmetry here and here at every step, if you combine them in a proper manner. Okay? And then you put another guy here, and so on and so forth. So essentially what you are doing, you are in the final description is a model, which can be very complicated. This is the problem. Okay? But has a gauge symmetry, which is inherited by simply the fact that you have used a global symmetry, but you have put it in small boxes. Actually, this is really equivalent of gauging, right? Take a global symmetry and make it local. Okay? And we will see, I will mention one example of this tomorrow. Okay? This has the price that the Hamiltonians are very complicated. But has the advantage that there are systems in atomic physics where you can have very, very bizarre global symmetries, even SUN. So this is something which is, in my opinion, the best method to go towards non-abelian models, even though nobody has ever demonstrated in an experiment. These, I will say, are the 4 possible methods that people develop. Yes?
What's the trick in like sewing those guys together? Like, because I mean, it seems to be very delicate in like how you're combining those things in these regions. Like
Okay, so let me give you an example, concrete example. This I want to keep, sorry. We do it there. Oh, actually, here. Now, this is a work that I was involved in, so I will try to present it without being too much biased. Okay? And the idea that we had was to use 2 types of atoms that you can trap independently. Okay? And for one type of atom, we proposed to use a lattice of this type. And then the other type of atom, as a lattice of this type. Okay? They are superimposed. So this is our gauge theory. And here we have a maximum, but here we'll have again a minimum. And this continues. Okay? So this you can do, for instance, if you have alkyl and earth atoms. It can be strontium, terbium. And the reason why you can do this in these atoms is because they don't have only a stable ground state manifold, but they also have a very long-lived metastable static state, which is the 3p0. And the reason why this is very long-lived is that the transition So the decay between this excited state and the ground state is doubly forbidden. So even if you put an atom there, it takes a lot of time before it decays. And typically, the time scales for that are of order of hundreds of seconds. Okay? This is, by the way, also the same transition that people use in clocks. Okay, it's a clock transition. Now, the advantage is that since these states are separated by optical transition, you can really trap them independently. Okay? So it's not inconceivable to design a lattice which is really like this. Okay? Where here, for instance, you can have the ground state atoms, and here you can have the 3p0. Okay? There are some subtleties in the sense that, of course, when you have excited state atoms, you can have a lot of inelastic collisions, but let's not forget about it for a moment. Now, what you can do, you can imagine that here you put one atom of this type, and here you put two atoms of this type. Okay? Now, these atoms will not be able to jump to the next triple well because there is a huge potential barrier. So locally, there is at least a U1 invariance. In fact, it is larger, but at least a U1 invariance. And here there is also U1 invariance. That's the definition of gauge theory. Then, can you write this as a theory where there is matter coupled to gauge fields? This is a different business. Okay? And then what you have to identify, you have to identify a set of operators that map correctly into the gauge theory. And this is, it's possible. Okay? So we wrote a work by Federica Sorace et al. It's a PRX Quantum 2023, where we analyze this in detail. Or this alkaline Earth-like atoms. This work is actually inspired by an older work that we wrote many years ago with Bajish Banerjee et al. Where actually we discussed this in two works. And this second work, we actually do it for SUN. Okay, it's really non-abelian. And the reason why you can do it non-abelian with this alkaline Earth-like atoms is that in principle you can add on top of this, also the nuclear degree of freedom for fermions, at least. For bosons, you cannot do that. And for fermions, this becomes an actually SUN symmetry, with n can go up to 10. Okay, it's bounded by 10. SUN theories start getting crazy. Okay, we were happy with 3. Okay, that's the reason why I believe that. If at some point there will be a quantum simulation or non-abelian theory, these systems and these kind of techniques are probably the ones which are most promising. Because the symmetry is there, and it's really good. I mean, people have tried to measure how these atoms violate this symmetry, and the violations are smaller than 10 to the relative violations are smaller than 10 to the minus 8. This is delicate business. Because, of course, you want to use, I mean, when we wrote the first theory paper, we say, okay, the experimentalists just find out a right amount of lasers and they do it. It turns out this is actually very complicated, okay? Because you have to find out what are the proper frequencies to do this with a minimal effort. And there is also an additional problem that we did not fully seriously consider in the earlier papers, is that when you write a lattice of this type, it's not that you simply have a Wannier function localized here, 1 year, and 1 year. This is actually not true. If you try to write down the block theory for this, it turns out that you will have Wannier functions which are delocalized over these triple wells. And they're very problematic. So one has to be very careful in saying, okay, you just put a potential and this will be a Hubbard model, blah, blah, blah. It's not true. You have to do a computation ab initio very carefully. And yeah, that's what is done also in this work. Huh? In this work, we really did the band theory for that. Good. So I told you everything now. Okay, no, now I tell you about the experiments. Okay. So the first, yes, let me do it here. So first of all, are there any other questions on this? No. Okay. So now what we will describe is what I say is the first experiment where people did the quantum simulation of a gauge theory. And this was in the group of Rainer Blatt by Esteban Martinez et al. And was in Nature 2016. Okay. So the theoretical idea for this is to study the Schwinger model by integrating out the gauge fields. Why? The reason is because in trapped ions, this is a trapped ion experiment. It is very easy to manipulate spin 1/2 degrees of freedom. Okay, so the basic degrees of freedom are spin 1/2. And of course, if you look at how we define the Schwinger model, we have this infinite dimensional Hilbert spaces for the gauge link. But the Hilbert space for the fermions at every site is just 2-dimensional. Okay? Of course, there are fermions, but there is a transformation known between fermions and spins in 1 dimension. It's called Jordan-Wigner transformation that maps one into the other. Okay? So this type of degrees of freedom look perfect to represent staggered fermions. Now, how does the integration of the gauge field work? And now I would like to do this in a bit more detail. Is essentially writing down these equations correctly. Okay? So suppose that you have a given boundary condition, okay? That EL is fixed. Then your second gauge field, E1, is given by EL minus N1, so the construction, the number operator at 1, and okay, I have not written Gauss law, but there will be also a shift due to Gauss law, which is equal to +1. Okay? So that's the form of E1. Now, if we try to write down the corresponding electric field part of the Hamiltonian, this will contain E1 square. So this we can write down by just looking at this combination of EL and EN. This will be EL, which is a constant, minus N1 plus 1 square. Then we have to do the same for the second gauge link. This will be equal to E1 minus N2. But E1 is given by this formula. We put it here. This will be equal to EL minus N1 minus N2 plus 1. And you go on with this. Okay? So the electric field of the second one will be E2 square, blah, blah, blah. At the end, what you get is that the electric field part of the Hamiltonian, apart from the boundary condition EL, which is just a number we don't care about, only depends on the various number operators. Okay? So it's something that does not depend on electric field anymore because we have integrated it out. This is cool because it allows us, this essentially, okay, we can raise it, to write down the Schwinger model up there as a model of only the ends. Okay? So this implies that H Schwinger is now only containing the psi's, psi degas, and n. But still, it's not enough because in trapped ions we have spin operators. So, and the idea is that then we transform this utilizing what is called Jordan-Wigner transformation, and the Jordan-Wigner transformation is saying the following. I mean, we are replacing fermions into spins, okay? Spin 1/2. So this implies that the spin Z operator at the site I is equal to twice Ni minus 1/2. And this is simple relation, but if you look at S plus, this is getting what is so-called, sorry, psi dagger I, a Jordan-Wigner string, okay? E to the I pi, bit L smaller than I, to Ni minus 1/2, okay? And the reason why you get this string is because this has to take care of the fermionic statistics. Okay? So with the integration of the gauge field and this Jordan-Wigner transformation, the Schwinger model turns into something which is like this. Okay? So H is equal to T sum over I, sigma plus I, sigma minus I plus 1, plus Hermitian conjugate. So this has become the first term, plus M sum over I, Mi sigma Zi. So this will be the mass term that will be staggered, but there will also be a small correction due to this integration of gauge fields. Plus, and this is the most interesting thing, there will be now the electric field. But the electric field square will only be made out of these sigma z's, and the expression is actually a bit complicated. This will be G squared divided by 2, sum over all the pairs I smaller than J, Cij, sigma Z I, sigma Z J. Okay? And this Cij is actually equal to N minus J. Okay, so this is the form of the interaction. Now, let us pause a minute and try to understand what this interaction is about. Okay? Or at least try to get some of its qualitative features. This interaction depends linearly on the distance J between the points. But what is amazing is that actually this is stronger at one boundary than at the other. Okay? So when J is close to the left boundary, J is small, this interaction is huge. Okay? When we are close instead to the other boundary, J is almost close to N, so this interaction is small. It's very anisotropic. The reason why it says anisotropic is because we have chosen to do the integration from one side with respect to the other. Okay? But it's large, it's always so large, anisotropic, and is also somehow fine-tuned in the sense that there is a common coefficient for all of them, but there is a very strong position dependence. So it is something that if we try to do it analog, we don't really know how to do. Okay? Then the idea is to try to put this directly on a quantum computer. So what they did, Esteban and collaborators, they did the Trotter approximation on this Hamiltonian. Okay? So something that we discussed yesterday. We wanted to study, for instance, the time evolution of a given state. We did the Trotter. Is the evolution. Okay. So what was the physics that we studied? And now I give you one example. Maybe it's worth having this one. Okay. So yesterday that we discussed, okay, this Trotter approximation works when the Hamiltonian is local. Okay. Well, it's not that local. everybody is interacting with everybody. Okay? And the strength is actually of order n. So it's not so clear that for a sugar model this works. However, you should think about it in a different manner. So if I do the trotterized evolution of this, or the trotterized evolution of the Hamiltonian that I've just cancelled, the formulas, they should be exactly the same. They are the same operator. We can do an analytic path between the two, right? By doing this Jordan-Wigner and this integration. This is not local, but this is local. Okay? And what does really matter is that actually this is only a very specific type of non-local interaction that can be mapped into a local theory. So for gauge theories, you can use Trotter evolution. Because you know that while the Hamiltonian that you might be looking at has some long-range interaction due to the fact that you have integrated out some gauge fields, it is the same as doing something which is actually fully local. Yes? Why it is like this? The reason is that one can see it from these expansions. Okay? Is that if I look at the electric field value of 1, this only contains N1. So it's a simple thing. N2, we will start containing N1 and N2 interactions, because there will be a square containing both. But look, but N1 and 2, it actually enters in all the electric fields. Because also if I have the electric field 3, will contain N1 and 2. When I square it, N1 and 2 will happen again. So the interaction between the first two bonds will appear n-1 times. Now, you can do the same reasoning and study the interaction between the bond at the site n and n-1, the last one. Okay? This only appears at the very end, in the last electric field. So this appears with the strength 1. And then, okay, this you have to believe me because I'm not proving it. This is happening less and less. Okay? The more you move. And this is a proof of this equation. But this is telling you that this is only for the nearest neighbor. If you go to the beyond nearest neighbor, you can do the same reasoning. Okay, when is the first time that N1 and 3 appears? It's when you take into consideration E3. And then it always appears. So N1 and 3 will have something similar with a -1. And this is the J. Okay? So the reason why this interaction appears is because originally there were this electric field square, and through the integration we get that. Yes? Yes? Like, are they like magically the same somehow? No. Exactly, no. I mean, the thetas are gone because after we have integrated out the gauge fields, thetas and L, they have completely disappeared. But the point is that we will have an Hamiltonian which contains the fermions, which in the ions we cannot do. So then, on top of that, we have to do Jordan-Wigner. The reason why Jordan-Wigner works without making a mess here is because the terms which are off diagonal in the fermions are only nearest neighbor. They were only appearing, I don't know why I canceled this, they were only appearing on the first term. If we would have had something which was psi x plus 2, we would have seen also a reminiscence of the string in the effective dynamics here. Yes? Okay. What we did, we applied on the already transformed thing. But formally, they are the same formulas. So in principle, you could do the same. Look, I suggest we take a break. I will use the next hour and a half to finish a bit and show you maybe some experiments, some results of this experiment, and then we will do the exercises, if the organizers agree. Unless there is questions. Similar question? Okay. Okay. Very good. Okay, see you later.